Good evening. Today we are in the week 12 of the lecture series Thermodynamic Classical to Statistical, and I am solving some problems, a sample problem that are going to help in the conceptual part also. So we will solve some questions related to that assignment 12, and I will start in 2 minutes and I'll wait for some if someone joins. Okay, so we will start it now. So I will start with some conceptual part and then move to that assignment question, and after that some sample problem that I have. So first of all, about the some formulas of thermodynamics. So basically I'll solve a few questions on work done and these delta, Gibbs free energy and internal energy, entropy, etc. So I'll be writing the formulas related to that, and after that I'll move to the question part. So we know the first law of thermodynamics. du is equals to dq plus dw, and its theoretical form is energy can neither be created nor be destroyed. Energy can neither be created nor be destroyed. It can only be changed from one form to other. And there are a few types of processes that we study mainly, like isothermal process. Like for isothermal process, and for ideal gas, what happened? Delta T is equals to 0 for isothermal process, and when temperature is not changing, internal energy is also not changing. That means delta U is also 0 for isothermal process. That means also delta H is equals to 0. So these are 0 for ideal gas. This relation are good only for ideal gas only, and these are change in internal energy and change in enthalpy is 0 for both reversible and irreversible reactions processes. Okay, so what will be the work done will be equals to the minus of, since we know del, if we convert it into the delta form, delta U is equals to Q plus W, so this implies delta U is 0, so 0 is equals to Q plus W, so W is equals to minus of Q for isothermal process for ideal gas, and both for reversible and irreversible Q is equals to minus W. Okay, so next, now work done. What is work done for reversible? We know that work done is equals to integration P dV from V1 to V2, that is equals to, this is P external, P is equals to for ideal gas PV is equal to nRT, so P is equals to nRT by V, so this is nRT by V dV integration from V1 to V2, so this is nR dV by V integration, so this is nR, sorry, T, nRT ln V2 by V1, this is work done. So, and this is equals to minus of Q for isothermal reversible process sorry, in ideal gas. Okay, now for irreversible, what happens if process is irreversible? Then work done is equals to minus P external delta V. Okay, and this is equals to minus Q only. And there, if free expansion is given, free expansion, for free expansion work done is 0, because free expansion P external is 0, so P external is 0, that means work done is equals to 0. So for free expansion P external is 0, that means work done is 0. True for both reversible and irreversible. Okay, now about the adiabatic process. Let me check the recording. Sorry, not the recording. Now let's just start for this, what we say, this adiabatic process. For adiabatic process, what happened for adiabatic process? Change of heat, there is no exchange of heat. For adiabatic processes there is no exchange of heat. So we know that for this isothermal process is PV is equals to constant, यानी कि PV P1 V1 is equal to P2 V2. But for adiabatic process it is not the true relation. So for adiabatic processes and ideal gases, there are three relations: P V to the power gamma is equals to constant, and T V to the power gamma minus 1 is equals to constant. We are going to use this equation in the questions, so please see it carefully. T to the power gamma, P to the power 1 minus gamma is equals to constant. So these are the three relations. They are all derived from this one, so you can derive from this one. And gamma, what is gamma? Gamma is Cp upon Cv. And what is the value of gamma for monoatomic and diatomic gases? For a monoatomic, gamma is equals to 1.66, and for diatomic, gamma is equals to 1.4. Now, what is the work done? Work done is equals to minus 1 over 1 minus gamma P2 V2 minus P1 V1. That's it. And we can say that for adiabatic processes, delta U is equals to W, since Q is equals to 0, so W is delta U. You can also calculate W by using delta U, since we know that delta U is equals to Cp dt. Okay, or NCP dt. EBT is a molar quantity. Sorry, and CV dt. This is CV, heat capacity at constant volume. So like this we can calculate work, and we can also use this formula. Now the process is irreversible. For irreversible adiabatic process, first for free expansion, again the work is 0, and we know Q is 0, and delta U will also be 0, because W is equals to delta U. So delta U, Q and W all are 0 for free expansion in irreversible adiabatic process. Now if P external is not 0, what will happen? Now delta U is equals to W, and this is equal to minus P external delta V, and also delta U is equals to NCV molar delta T. So we can use this. Okay. Now for isothermal, PV is constant, and for adiabatic, PV to the power gamma is constant. Okay, so now if you plot log P versus log V, how the curve will look? For this one, log P plus log V is equal to log C, some constant. But for this one, log P plus gamma log V is equal to log C. So now if we plot log P versus log P on y-axis, let me erase some part. Okay, if we plot log p on y axis and log v on x axis, log v on x axis and log p on y axis, then according to y is equal to mx plus c, this is log p is equal to minus of log v plus log c. So this is intercept and this is the x axis, so this is slope minus 1 only. So this is like, let's say it is starting from here, log c, this is log c, and it is a straight line coming down. Okay, this is for iso. Now for this one, gamma is always greater than 1, so slope is minus gamma, because log p is equals to minus of gamma log v plus log c. Again the intercept is less than log c only, and the slope is more, so this will come below like this will be area. So something like this. If we consider it is not on 0 scale, then it is this isothermal process. This case is true for expansion only, like log v, volume is increasing only, like from v1 to v2 expansion. If v1 is greater, v2 is greater than v1, then this one is true, iso and adia. Okay, but for the compression part, this will go backward, so we can say that log iso will be below, to the adia. So adia will be above and iso will be below. Two parts of the same curve. This is for compression and this is for expansion. If we are going back side, then this will happen. It means if we let's say we plot an axis like this, this is log v, this is positive side and this is negative side. This is log v, okay, this is negative side and this is positive side, so this will be like this only. This is for compression, this is for expansion. Iso above in expansion, iso below in compression. So we can say work done for adiabatic process is less than work done in for expansion, work done of iso is greater. Okay, because PV slope we can see this, work done of iso is greater for expansion, but for compression work done for adiabatic is greater than work done of iso for compression. So these are very important things that come in most of the competitive exams. They ask these questions directly about the slope, about the values which come below and which come above, curves, these curves, and these values of this work done. So it may be helpful. I'll write in here again what we get. Work done for iso is greater than work done for adia in expansion. Work done for adia is greater than work done for isothermal for compression. We can see it by PV curve, and work done is nothing but the area under the PV curve. So that too I showed only the log P versus log V, if we plot P versus V, it will be the similar only, like just the curve will be there like this only. If for expansion, let's say this is for ADIA and this is for this isothermal. So again for compression it will be like this only. So this is adiabatic and this is isothermal, V versus P, and the area under the PV curve is only the work. So area under the curve is more for adiabatic in compression and more for isothermal in expansion. So like this we can say that work done for isothermal process is greater in expansion and work done for adiabatic process is greater in compression. These are very basic things and these are asked many times in the exam. Now next thing that is important for today's questions is this Clapeyron equation. So we know that dP by dt is equals to delta H upon T delta V. So this is the Clapeyron equation and we can derive Clausius Clapeyron equation from here. So Clausius Clapeyron equation is ln P1 by P2 is equal to delta H upon R 1 minus, this is transition, 1 minus T2 minus T1. So this is the Clausius Clapeyron equation. Next thing, one more thing that is important is this Maxwell's square and the equations, Maxwell's equations. So that I have shown in many classes. Again I will solve this Maxwell's square. So this ST SP VT, this is the square, HG AU, these are the functions. So DH is equals to for solving DH we need to write DS and DP. So DS DP, like from both sides, this is DS and P, so we take DS and DP. Now from S to we are moving along this arrow. So from S to this is going towards T and arrow is pointing towards C, so it is positive. Now from P we are going towards V and arrow is pointing towards V also, so it is positive only. So this is VDP. For DG, this is equals to DP, this one, and DT. So okay, sign I don't know now, so sign will check. So from P we are going to V. So from P we are going to V and arrow is only towards V only. From T we are going to S and arrow is towards, not toward S, so it is minus. Now DG is done. Now DA is equals to DT and DV, DT and DV. So DT, from DT we are going, from T we are going to S and arrow is not toward S, so it is minus SDT. From V we are going to P and arrow is not towards P, so it is minus PdV. So it is minus SDT minus SP minus PdV. Now for the DU is equals to DS and DV, and from S we are going to T and arrow is towards T, so positive. From dV we are going to P, and arrow is toward, not toward P, so it is minus P dV. Minus P dV plus T ds minus P dV. Okay, so these are the four equations. Now we know for exact differentials, they are state functions, and all these H, G, A, U, these are all state functions. For such functions, if let's say this is Z, so Z is a state function. For such function, if we are differentiating with respect to X and then differentiating with respect to Y, it is equals to if we differentiate first with Y and then with X. So this is equal. So this is keeping Y constant. First Y constant and then X constant. Here first Z constant and then Y constant. So page now. But other thing we can study from here. These things we know about them. Again, we can solve the problem related to entropy. So I have written in many lectures about the entropy. It is very important function as well. Change in entropy, it is asked in nearly every exam. So these formulas are very important. So for like if process is reversible and gas is ideal gas, and temperature and pressure is temperature and volume is given, then delta S is equals to, in terms of temperature and pressure, N CV ln T2 by T1 plus NR ln V2 by V1, and in terms of temperature and pressure, delta S is equals to NCP ln T2 by T1 plus NR ln P1 by P2. And if temperature is constant for isothermal process, delta S is equals to NR ln V2 by V1, that is equals to NR ln P1 by P2. Okay. And what if the volume is constant, then this will be 0. If volume constant, if pressure is constant, this will be 0. If pressure is delta P is 0. So we can only solve these parts to get the entropy part. So these are the formula for entropy. And if phase transition is happening, if phase transition is happening, then delta S is equals to Q by T. So this Q is enthalpy of transition, and this temperature is temperature of transition. So delta H of transition divided by T of transition. This is the entropy. and we know that reversible adiabatic processes are isoentropic because dq is 0. So we know that q is 0, then this delta S is equals to 0. Since this is 0, then this is also 0. Now entropy of mixing. For entropy of mixing of ideal gases, what we use? Delta S of mixing is equals to minus nr summation xi ln xi. Xi is the mole fraction. Now entropy of mixing is always negative. We can consider this. If three gases are mixing, then entropy will be negative only. So we can consider this. What other thing we can study here? Apart from this, in statistical, this was for the thermo part, classical part, and now for statistical part, we will write some formulas for statistical part. I'm sorry, try to join again. So now to the statistical part. Most important thing in statistical is distribution. And I have talked about this in my previous tutorials as well, on the formula for distribution of distinguishable particle and indistinguishable particle, and for those Maxwell-Boltzmann statistics, Bose-Einstein statistics, and Fermi-Dirac statistics. And I will be doing it again today, as it is the last lecture. So I will focus on revising the most of the part that we have talked till now, and then I will solve the questions. I have only 15 questions today, 15 or 16 questions today. So I will finish this part, and after that I will solve that. Maybe I will take another 20 or 20 minutes for this conceptual part, and after that I will start the questions. So distribution, let's say distribution of this distinguishable particles. So for distinguishable particles, let's say there are m states and n number of particles. So how many how many distributions are possible then? If though there is no restrictions, they can be arranged in m to the power n ways. So all the arrangements are m to the power n times. If let's say we have restrictions, and let's say there can be only one particle in one state, so what now? The distribution will be the permutation only, m p n. So m factorial divided by m minus n factorial. This is when one particle is in one state. What if the occupation number is given? These are very important formulas. You can just listen to these formulas and apply according to the question, and you can get the distribution very easily. They have been asked in many last year questions, like last year papers, GATE, NET, JAM and all, TIFR also. So they ask these questions directly. If we know these things, you can easily apply this and get the answers. So now if occupation number is given, what then? Let's say there are n total particles. And there are n1 in first state, n2 in second, n3 in third, and ni in ith state. So what will be the distribution? And let's say the degeneracy for all, gi for all is 1. So what will be the formula? Then w will be equals to number of, if n is the total number of particles, then n factorial divided by n1 factorial, n2 factorial up to ni factorial. This is equals to n factorial into multiplicative of ni factorial. So this is the formula if occupation number is given then, and degeneracy is 1. What if degeneracy is also given? For each state there is degeneracy. So let's say for n1, n2, n3 up to ni are the number of particles in I states, n is the total number of particles, total number of particles, and g1, g2 up to gi is the degeneracy of ith state. Each state degeneracy, for first state g1, for second g2, and ith state gi. So degeneracy is given. What will be the formula for w then? W will be equals to n factorial into multiplicative of gi to the power ni divided by ni factorial. So this is the formula. Let's say let's we solve a question for this conditional problem. Let's say degeneracy is given and also the occupation number is given. Then how we solve the question? Let's say there are 6 states, and occupation of both all the states are 0, 1, 2, 2, 5. Let's say 2, 2, let's say 3 and 1, 1, 2, 3, 4, 5, 6. These are the 6 states. And degeneracy is, let's say 1, 1, 2, 2, 1, 2. Let's just randomly I am giving this. So this is the occupation number of each state, and this is degeneracy of each state. So what will be the w? W is equals to n factorial. Total number of particles are 3, 1, 4, 3 to 5, 1, 6, 2, 8, 1, 9. 9 particles are there. 9 factorial divided by gi. So we need some space here actually. So I'll rub this and then solve. or I'll solve in next page. That will be much easier and much easy to understand. So W is equals to, there are 9 total particles, so 9 factorial. In first state degeneracy is 1, so 1 to the power ni number of particle in first state is 0, this is 0 occupation number, and 1 is degeneracy, divided by n1 factorial, so 0 factorial, into, this is a multiplicative operator, so this 1 is the occupation number and 1 is the degeneracy, so 1 to the power 1 divided by 1 factorial, into the next state degeneracy is 2 and particles, number of particles is 2, so 2 to the power 2 divided by 2 factorial, and in next state again 2, so this is 2 to the power divided by 2 factorial. In next state it is 3 1, degeneracy is 1 and number of particles is 3, so degeneration to the power 3 divided by 3 factorial, and then degeneracy 2 and occupation is 1, so 2 to the power 1 divided by 1 factorial. So this is the distribution for this condition. So like this, any type of question, whether it is very difficult or easy, you can solve it very easily. So this is how it works. Give me a minute. Now also this formula, this that we have used, this is in accordance to the Maxwell-Boltzmann distribution. This is Maxwell-Boltzmann distribution. Now, if the particles are indistinguishable, for indistinguishable particles, and let's say there are again m states, n particles, and let's say there is no restriction, then distribution is number of microstate is n plus m minus 1 factorial divided by n factorial m minus 1 factorial. So this is nothing but the Bose-Einstein statistics. We know that in Bose-Einstein statistics, any number of particles can occupy any state. So for such distribution, the number of microstate is given by this formula. Now for if there is restriction, if one particle, only one particle can occupy one state, then it will be nothing but the combination only, m c n, m factorial divided by n factorial m minus n factorial, and this is nothing but the Fermi-Dirac statistics. So all the fermions follow this one and all the bosons follow this one, and we have discussed this many times. So I'll quickly move to the next thing now. The next thing is this partition functions. So the partition function, we will write the formulas for them. Before that, we should know about these ensembles. Important type of ensembles are microcanonical, canonical and grand canonical. And what are the properties for them? For microcanonical, number of particles, volume and energy are constant. NVE is constant. For canonical, NVT constant. Temperature is constant, energy not. And for grand canonical, mu Vt is constant. Mu is chemical potential. And we know that Q is partition function and it is summation of levels into degeneracy into e to the power minus ei upon kBt. And at t is equals to 0, this is nothing but e to the power minus infinity, and e to the power minus infinity is 1 over e to the power infinity, and which is equal to 1 over infinity. 1 over infinity is 0. So this is all equals to, again let at t is equal to 0, e to the power gi. Okay, so it is equals to, at t is equal to 0, it is g0 e to the power, we know that it is g0 plus g1 e to the power minus ei upon e1 upon kBt plus g2 e to the power minus e2 upon kBt and so on. So this part remain and all the other part will be 0. So this is 0 at t is equal to 0, and q is equal to g naught, degeneration of ground state. And if temperature is infinite, then this gi e to the power minus ei upon kBt is equals to g naught plus g1 e to the power minus e1 by kBt plus g2 e to the power minus e2 by kBt and so on. So this is, temperature is infinite, so this is e to the power minus 0, and e to the power minus 0 is e to the power 1 over e to the power 0. So this is nothing but same only, 1 only. So this is g naught plus g1 plus g2 and so on. So this is summation of gi. At temperature t is equal to infinite, q is summation of g, degeneration. The formulas for all the partition functions: q translation, rotation, vibration, and we know that q is multiplicative. So q is q translation, q rotation, q vibration, and q electron, multiplication of these. And energy is additive. So E total is E translational plus E rotational plus E vibrational plus E electron. Now the formulas for this, all the Q's. Q translation is equals to 2 pi m kBt to the power divided by h square to the power 3 by 2 into V. And we can write it as V by lambda cube, where lambda is 2 pi m h upon 2 pi m kBt under root. This is Q translation. Q rotation is kBt by sigma hcb, where B is h upon 8 pi square IC. Okay, you can write it as T over sigma theta B, theta R. So characteristic rotational temperature. Sigma is symmetry factor, and which is equals to 1 for heteronuclear and 2 for homonuclear gases. Now Q vibrational this is e to the power minus, if we consider it in two cases, Q vibrational we consider in two cases. If we consider E0 as half h nu, and if we consider E0 as 0, like if we can take 0 point energy as 0, and if we take exact 0 point energy, that is half h nu, then the formula is Q vibrational is equals to e to the power minus h nu by 2 kBt divided by 1 minus e to the power minus h nu by kBt. We can write it as e to the power minus theta by t, theta by 2t, and e to the power minus theta by t. And if there is 0 point energy is 0, then Q vibrational will be 1 over 1 minus e to the power minus theta by t. That's it. And where theta is h nu by kb. And electronic, Q electronic we know that is equals to summation of Gi e to the power minus Ei upon kBt. Okay, so now we are good to go for the questions, and also we can write this entropy formula, sorry, enthalpy, internal energy formula, that is equals to kb n kBt square curl by curl t of ln q at constant volume. This is internal energy for a system. And from here, if we differentiate it with respect to temperature, sorry, if we at constant volume, this will give Cv. Heat capacity we can calculate from here. Okay, so now we will solve the questions. We'll start in 2 minutes, just a 2-minute break. I'll check whether it is going fine or not, recording and all. Okay, so let's start again. Now we will solve some questions. So the first question, a sample of an ideal gas with initial pressure P and volume V is taken. Okay. A sample of initial pressure P and volume V is taken through an isothermal expansion process, during which the change in entropy is to be delta S. So delta is the entropy change, pressure P, volume V. And if the universal gas constant is R, work done by the gas is given by. So we need to calculate W. And this is isothermal expansion. So isothermal, we know that delta U is equal to Q plus W, and for isothermal delta U is equal to 0, Q is equal to minus W. Maybe that can help. Let's see. And so delta S is equal to Q upon T. So we can write it as W upon T. So that might help, I think. So W is minus delta S into T. Okay. Work done by the gas is given by. So the formula says PV delta S upon NR. So T is there. So T for an ideal gas, PV is equal to nRT. So T is PV upon NR. If we put it here, W is equal to minus delta S into PV upon NR. So is there any option like this? So this is PV minus, so okay, this minus is here, so there is no minus in option. We are making any mistake. So this is expansion, and for expansion delta S is positive. So this would be minus delta S PV upon NR. Let me check in the question, in the assignment. This is from the assignment only. So let me just check this. No. Okay. So maybe there should be a minus sign there. A sample of gas, the P and V is taken through an isothermal expansion. Isothermal expansion is there. During the change in entropy is delta S, and we know that for isothermal expansion, du for isothermal expansion of an ideal gas, this is W is equals to minus Q, and delta S is equals to Q upon T, and this Q, if we substitute by minus W, so this is delta S is equals to minus W by T, and delta S is equals to minus W T. So from this we PV is equal to nRT, so T is equal to PV upon NR. If we put here, so PV upon NR into delta S is equal to minus of W. Universal work done by the gas. Okay, work done by the gas. Work done by the gas is minus W. So we know that work done by the gas is negative and work done on the gas is positive. Work done by the gas is negative. So this the minus W is work done by the gas. So this is the correct option. Now the question number 2, Cp greater than Cv is given. Why is okay? Where Cp is specific heat of gas at constant pressure and Cv is specific heat of a gas at constant volume, because at constant pressure the attraction between the molecule is larger, the coefficient of expansion differs, work is done by the expanding gas, none of the above. For the reason for Cp greater than Cv, we know that delta H is equal to delta U plus P delta V, or we can say delta U minus W. So this is, they are saying work is done by the expanding gas. So work done by the expansion is, we know, negative. So this is negative quantity, so this will add only. So delta U plus something. So this is delta H is greater than delta U here. From this expansion thing we are getting delta H is greater than delta U. This implies if we change it in NCP, delta T is greater than NCV delta T, and if we balance these sides, Cp is greater than Cv. So this is only just because of the property that work is done by the work is expansion. So for expansion work, delta H is greater than delta U. So for compression it may reverse, because for compression work done is positive and this quantity will be differentiating from this delta U, and delta H will be less than delta U then, and the whole scenario will be reversed. So for this case work is done by the expanding gas. So work done by the expansion, then Cp is greater than Cv. Okay. Question number 3. So an electric current of 3 ampere flow through a rod of resistance of 10 ohm. It is being cooled by running water and its temperature and is kept at a temperature of 300 Kelvin. Okay. Delta T is 0. The change in entropy per second of the resistance is, so delta T is 0, and we know that it is a solid, so delta V also 0, and we cannot change pressure, so delta P also 0. So T, P and V all are constant, so there is, and also there is not any phase transition because state are same. No conversion from solid to liquid or gas, so all the states are same. That means that there is no change in entropy. So delta S is 0 since there is not any change in the state of iron of the rod by this current flow. So we can say that delta S is equals to 0. So delta S is equals to 0. This is just a tricky question, just a conceptual question, since there is no change in temperature, pressure and volume. Since this is an solid thing, so there is no change in volume and there is no change in pressure, and temperature is also given constant. So and also there is not any transition from one phase to other, so we can say that entropy change is 0. A 3-level system of n atoms with energy minus E naught, 0 and E naught. Okay, 0, E naught and minus E naught. This is the 3-level system in thermal equilibrium at temperature T. Okay, let beta is temperature T and beta is equal to 1 over kBT. If beta E naught is equal to 2, this is given, the probability of finding the system in level E is equal to 0. Okay, probability of finding the system in 0th level is n0 divided by, and 0 is 1. This is ground 0 level, this is 1 level, 0 is 2 level. So P at 1 level is n at 1 divided by n at 0 plus n at 1 plus n at 2. So we can write it as e to the power minus E1 divided by kBt divided by e to the power minus E naught by kBt, e to the power minus E1 by kBt plus e to the power minus E2 by kBt. So this E are E of 0 state, first state and second state. So by putting the values, this is E0 and this is E1. So E1 is 0, so e to the power minus 0 divided by E naught is minus E naught. So this is e to the power minus E naught by kBt plus e to the power 0 plus e to the power minus, okay, it was minus E naught, so it is minus plus E naught. Okay, and this is minus E naught divided by kBt. Since this is E naught and this is minus E naught, so this will become e to the power minus into minus plus E naught. So e to the power 0 is 1, and it is given that beta E naught, that is E naught by kBt is 2. E naught by kBt is given 2. Beta E naught is equal to E naught by kBt, and which is given equal to 2. So this is e to the power 2 plus 1 plus e to the power minus 2. Okay. Now P of first level is 1 over E square plus 1 plus e to the power minus 2, and this formula is given, e to the power x plus e to the power minus x is equal to twice of cos hx. So we can use on this 1 over e to the power 2 plus e to the power minus 2 plus 1. We can write it as such like this only. This is twice of cos s 2 plus 1. This is equals to 1 over 2 cos h of 2 plus 1. Or we can say this is P1 is equal to twice of cos hyperbolic 2 plus 1 to the power minus 1. 1 plus 2 cos hyperbolic 2 to the power minus 1. So this first one is correct. Now the next question. According to theory of equipartition of energy, if a system is in thermal equilibrium at a temperature T, then each independent quadratic term contribute how much energy to the total energy value. So we know that according to equipartition law, you can say that an equal amount of energy will be associated with an equal amount of energy will be associated with the each degree of freedom. And we know for one particle, for each particle, let each particle, there are 3 degrees of freedom. Okay, if we consider only 1 degree of freedom, then for one particle and 1 degree of freedom, the contribution is half kBT. Okay, so if we write it in form of this gas constant, and we know that for one particle this is kb, for Na particle it is Na kb, which is equal to R. So R is for 1 mole and kb is for 1 particle. So if we replace kb by R, so kb is equal to R by Na. Na is Avogadro number. If we put it here, so this is equal to half R by Na into T. So RT by 2 Na. So RT by 2 Na. So this is the option for 1 degree of freedom. If you consider all 3 degree of freedom, then it will be 3 by 2 RT by Na or 3 by 2 kBT. So it is according to the equipartition law of energy, that each equal amount of energy is associated with each particle and each degree of freedom. Next question. For the reaction is given, value of delta U is given and delta S is given. Okay, delta G need to be calculated. So delta G is nothing but delta H minus T delta S, and delta S is given, delta U is given, delta H is not given, delta U is given. So we will use this delta U to calculate delta H and put it here. So given quantities are delta S is equal to 84 joule per Kelvin, and temperature is 298 Kelvin, delta U is 9 kilojoule. So we know that delta H is equal to delta U plus delta Ng RT. And in this process, what is delta Ng? Delta Ng is number of moles in the number of mole of gas in product minus number of mole of gas in reactant. So this is 2 minus 1, this is 1. So delta Ng is given. Delta U is 9 kilojoule plus delta Ng is 1. R is 8.314 joule per Kelvin per mole. Temperature is 298. This is in joule. So if we divide it by 1000, it will become kilojoule. So now the units are balanced. Now if we solve this, 8.314 into 298 divided by 1000, this is 2.4775 and plus 9, so this is 11.448 kilojoule. Delta G, if we put this value in here, so delta G is equals to delta H minus T is 298 into this delta S is 84. This is joule per Kelvin, so we can divide it by 1000, so it will be in kilojoule also. This is in kilojoule, so all the units will be balanced now. 298 into 84 divided by 1000, this is given 25.032, and this is 11.48 minus 11, 25.032, 11.48. This is minus of 13.552. Okay, this is minus of 13.55 kilojoule. Option C is correct. Now to the next question. a given mass of gas is a given mass of gas at 0 degrees Celsius is compressed reversibly and adiabatically. Okay, process is adiabatic process. And the pressure is 20 times. Okay, reversible compression, adiabatic, reversible compression. And pressure, let's say initially it was P naught and then it is 20 times, so 20 times P naught, so this is P1 and this is P2. Now temperature T1 is given. T1 is 0 degrees Celsius, that is 273 Kelvin, and T2 we need to calculate. Gamma is given, this is equal to 1.42. Okay, so let's calculate it. Now I just wrote, I think in my first or second slide, that T to the power T, okay, this is T and P. Okay, T to the power gamma, P to the power 1 minus gamma is constant. For adiabatic processes, T to the power gamma into P to the power 1 minus gamma is constant. So by applying this formula, we can easily calculate the temperature T2. So according to this, T1 to the power gamma, P1 to the power 1 minus gamma is equal to T2 to the power gamma, P2 to the power 1 minus gamma. T1 by T2 to the power gamma is equal to P1 by P2 to the power 1 minus gamma. Now putting the value, so T1 is 273, T2 we need to calculate, gamma is 1.42, that is equals to P1 is P naught, P2 is 20 P naught to the power 1 minus 1.42. Let me see it again. Okay, I have made a mistake. This is P2 by P1 and this is 20 P naught by P naught, so it will cancel out. So this is 273 by T2 to the power 1.42 is equals to 20 to the power minus 0.42. So we can solve this. Okay, now let's take log on both sides. So 1.42 log of 273 divided by T2 is equals to 0.42 log of 20. So let's say this log base 10. You can solve this. Can be solved very easily. So we can write it 1. Okay, log 273 minus log T2 is equals to 0.42 divided by 1.42 log of 20. Okay, let me use the calculator. Okay, just eliminate it in one side and then I'll calculate it in one go. Okay, log T2 is equals to, if we take minus sign here, then that will be plus, that is log 273 plus 0.42 divided by 1.42 log 20. So solve this quantity. Log 20 is 1.30 and 20 log is 1.3 into 0.42 divided by 1.42. So this all quantity is 0.3848 and 273 log is 2.43616. So this is coming as 2.82096. I'm taking last till last to get the near exact answer. So taking to the power 10, this is coming 662.159. So this is not 662. So let's say there are, we have considered it some approximation. So this is 660.21 Kelvin. Okay. Okay, if we take it 10 to the power 2.82, then it is giving 660.2. So if we take some approximation, then we are getting a right answer. So answer is 660.21. I just took 10 to the power 2.82 and it is given 660.69. If we neglect these quantities, it is given 660.69. So this is approximate answer. So it is option A is correct. Now the next question, a sample of 2 moles of an ideal gas O2 at 500 Kelvin is extended from 5 liter to 50 liter under adiabatic and reversible condition. The change in internal energy is close to. So we need to calculate the change in internal energy, that is delta U, and number of moles is given, number of moles 2, and temperature is given 500 Kelvin. Volume V1 is 5 liter and volume V2 is 50 liter. Adiabatic condition. So this is temperature T1, temperature T2 is not given. Okay, and we need to calculate delta U, and CV is given. CV is 2.5 R. This is molar, and we know that delta U is nothing but NCV molar delta T. So we have this quantity, we have this quantity, we need this quantity. We just solve one similar question to calculate temperature at one temperature is given and another temperature we have calculated. So this time we are going to use Tv to the power gamma minus 1 is equals to constant this relation. So T1 V1 to the power gamma minus 1 is equal to T2 V2 to the power gamma minus 1. This implies T1 by T2 is equals to V2 by V1 to the power gamma minus 1. And this is diatomic gas. So for ideal diatomic gas, gamma is Cp by Cv. So this is 7 by 2 divided by 5 by 2. So this is 7 by 5 and this is 1.4 only. So gamma is 1.4. So by putting the values, 500 divided by T2 is equals to V2 is 50 by 5 to the power gamma is 1.4 minus 1, that is 10 to the power 0.4. So T2 is 500 divided by 10 to the power 0.4. So just calculate this value. 10, okay, 0.4, 10 to the power 0.4 is 2.511. So 2.5 we can consider this. This is 200. Temperature T2 is 200 and temperature T1 is 500. So delta T is, okay, seems like there is some mistake. Okay, let's check this. Delta T is minus 300. So delta T is minus 300 because okay, let me erase some part and solve this. So we get T2 is 200 and T1 is 500. Now it is easy to calculate this CV, okay, delta U, since we have all the values. So now T2 minus T1 is 200 minus 500, that is equals to minus 300. This is equal to delta T, and delta U is NCV delta T, CV molar, and number of moles here are 2. CV is given 2.5 into R, and delta T is given minus 300. So this is equal to minus, if you multiply R, that is 8.314. So this is 2 into 2.5 into 8.314 into 300 divided by, this is 12471 joule, and we can write it 12.471 kilojoule. So this is 12.5 minus delta U. Okay, next question. Which of the relations is correct? With this equation is given, this is from Maxwell square, this relation is given, and we need to find which one is correct in this. So we can calculate by, since we know dg is equal to v dp minus s dt, this is given, and we know that g is a state function. It is not, it does not depend on path, and it is a state function, though it is an exact differential. This means that according to the exact differential, if z is a function and we differentiate it with one quantity first, that will be equals to if we differentiate it with respect to other. Like this. So here g is function of v and p and t. So we can differentiate g with respect to p first at constant temperature, and then with respect to t at constant pressure. Also this will be equals to if we differentiate it with respect to t at constant pressure, and then differentiate it with respect to p at constant temperature. So this should be equal. So we need to solve this and then find out which one is matching in the options. So we will solve it one by one. Okay. Now first let's say curl G by curl P we are solving. So with this relation at constant temperature, so delta T will be 0, this term will be 0 at constant temperature. So curl G by curl P at constant temperature will become V curl P by curl T. Okay. Sorry, curl P by curl P. So this will cancel out. So this is equals to V. Now if we differentiate curl G by curl P at constant T with respect to T at constant P, then it will give curl V by curl T at constant pressure P. So this is equation 1. Now if we differentiate it other way, like differentiate G with respect to T, first at constant pressure P. So at constant pressure this will be 0, and if we are differentiating with respect to T, then it will become minus S. Now differentiate this one with respect to pressure at constant temperature. So this will give curl S by curl P at constant temperature. This is equation number 2. And since we know it is a state function, so this both terms are equation 1 and 2 are equal. So left hand side is equal, then right hand side will also be equal. So this will be giving curl V by curl T at constant pressure is equals to minus curl S by curl P at constant temperature. So let's just see in the options. Curl V by curl T at constant pressure is equal to curl S by curl P at constant temperature. No, minus sign is not there, so this is not correct. Curl P by curl V, curl P by curl V at constant, curl T by curl S, no, not correct. Curl V by curl T at constant pressure is equal to minus curl S by curl P at constant temperature. So this is the correct answer. So answer 3rd is correct. Now to the next question. So the question says for the reaction N2 plus 3H2 give twice of NH3. Change in entropy for the system is given and the enthalpy of the reaction is given. Calculate the entropy change of the universe. So we know that delta S of universe is equals to delta S of system plus delta S of surrounding. So this is given, this is not. So we need to calculate this and add, and then we will get the answer. And what is given here? The enthalpy of the reaction, delta H of reaction is given, that is minus 1.91.8 kilojoule. And we know that in a reaction amount of heat that is given out, this is given for the system, and this heat is just opposite to the delta H of surrounding, that is equals to delta H of surrounding is equals to minus plus 91.8 of kilojoule. And we know then delta H of surrounding will be delta H of surrounding divided by T. So this is 91.8 divided by T is 298, and this is in kilojoule per Kelvin. So multiply by 1000, this will give joule per Kelvin. So just calculate this. (91.8) into 1000 divided by 298. This is giving 308.05 joule per Kelvin. Now delta S of uni is equals to delta of system is minus 197 and then plus 308.05. So this is equals to 111.053 joule per Kelvin. This is positive delta S of universe. So entropy of universe is positive. That is what we know. Entropy of universe always increases. Okay, now the next question. Okay, we are left with 5-6 questions are left. 1, 2, 3, 4, 5, 6. 6 questions are left. Let me check the recording once. Yes, it is recording. And the meeting, no one is here. Okay, so we'll start the question. The reaction is given N2 gas, 3H2 gas giving 2NH3 gas, and the data for entropy is given for all the individuals, reactant and products. Calculate the entropy change for the process and comment on the sign of the property. Okay, so delta S of reaction is equals to S of product minus S of reactant. Okay, so product side, this is twice of ammonia, so that is 2 into the data is given 192.3 minus this side 3H2, thrice of H2 is how much is for H2, this is 130.6, then minus N2 for N2 it is 191.5. so we'll calculate this. 192.3 into 2, this is 384.6, 3 into 130.6, this is 391.8, and this is 191.5. so 384.6 minus 391.8 minus 191.5, so this is minus of 198.7 joule per Kelvin per mole. So the sign is negative, entropy of the reaction is negative, and we know delta G is equal to delta H minus T delta S. Since this is negative, so this will become positive. Now it depends on delta H. So delta H now should be greater than T delta S, and it should be negative. In negative, it should be greater than T delta S. So then only delta G will be negative and the reaction will be spontaneous. Next question. Vapor pressure of a solid selenium is given by log P. Okay, and this is given log P, and for liquid selenium it is given by this formula. So for solid, log P is equals to minus 7440 by T plus 12.78, and for liquid, log P is equals to minus 5390 by T plus 8.63. We need to calculate the triple point temperature. Okay. So at triple point, pressure, volume and temperature is same for all phases. So we can equate equation number 1 and 2. So by equating this, 7400 by T plus 12.78 is equals to minus 3.90 by T plus 8.63. When solve this, so this is 7440 by t minus 5390 by t. So if we take this side, then this is 12.78 minus 8.63. So this is, let me calculate, 7440 minus 5390. This is 2050 by t. So this is 2050 by t, that is equals to 12.78 minus 8.63, 4.15. So temperature T is 2050 divided by 4.15. So this is given 493.98 Kelvin. So this is 493.98 Kelvin. Option 3 is correct. We can calculate by putting this temperature value in any of these equations. We can calculate P also. Okay. Since P and V, PVT, they will have only one value at this triple point. Next question. The first excited state of fluorine lie at energy of this above the ground state. Okay, ground state is 2p 3 by 2. First excited state is 2p 1 by 2, and this energy gap is given 420 per centimeter. The fraction of fluorine atom in the first excited state at kBt 420 per centimeter is close to, so fraction of in first excited state. So okay, n1 divided by n0 plus n1, we need to calculate this. Fraction of n1 in first particle in first excited state. So this is equal to e to the power, okay, g1 e to the power minus e1 by kBt divided by g naught e to the power minus e naught by kBt plus g1 e to the power minus e1 by kBt. Now from these two we can calculate the value of g. So g is 2j plus 1. For this j is 3 by 2. So j is 3 by 2 and j is half for this. Since we know that this is 2s plus 1 Lj, this notation 2s plus 1 Lj. So this j will give the degeneracy. So by putting the value here, 3 by 2, this is 4. G is 4 for the ground state and G is 2 for the first excited state. So this is 2 e to the power, E1 is given 420. So 420 divided by kBt, kBt is given also 420. So this is minus 420 by 420, this is 1, e to the power minus 1. And here G naught is 4, E naught, let's say it is 0. Then it is e to the power minus E naught, e to the power 0, then 1 plus 2 e to the power minus 1. So this is 2 e to the power minus 1 divided by 4 plus 2 e to the power minus 1. If we divide it, this will give e to the power minus 1 divided by 2 plus e to the power minus 1. If we take e to the power minus 1 common, so then it will be e to the power minus 1, e to the power minus 1, 2 divided by e to the power minus 1 plus 1. We can write it as 1 over 1 plus 2e. 1 over 1 plus 2e. So this is the answer. The next question, at room temperature thermal energy is, okay, the thermal energy is nothing but the kBt. kBT is thermal energy. So we need to calculate kBT at room temperature. So room temperature is 298 Kelvin, 25 degrees Celsius, that is 298 Kelvin. So energy is kb Boltzmann constant, that is 1.38 into 10 to the power minus 23 into temperature is 298 Kelvin. So this is in energy, this energy is in joule. So we need to calculate in per centimeter, and we know that E is equal to hc upon lambda. So we need in unit of 1 over lambda, so we need to multiply it by hc and we will get the units. So if we multiply it with the h, that is 6.626 into 10 to the power minus 34, c, that is 3 into 10 to the power minus 8, 3 to 10 to the power 8 hc, and this one 1.38 into 10 to the power minus 23 and 298. So this will give in per centimeter only. Let's just check these units. This is joule second, this is meter per second square, this is kb, joule per Kelvin, I think. This is joule per Kelvin, okay, हाँ, joule per Kelvin, and this is Kelvin, okay. So Kelvin cancel out. This would be per joule, okay. Okay, let's do it again. E is equal to hc upon lambda, and okay, I am doing it wrong. We know E is equal to hc upon lambda, and this is the value for this. Let's multiply this 298 into 1.38. So this is 411.24 into 10 to the power minus 23. This is in joule, okay. So now if we divide this quantity by hc, we will get in answer in per centimeter if we use centimeter only. Now this is joule per second, and if we use meter per second, centimeter per second square, okay, sorry, c is in centimeter per second, so this h is joule second, so this will cancel out and this joule will cancel out, then it will be in centimeter. So by putting the values now we can get the answer. H is 6.626 into 10 to the power minus 34 into C is, now this is in centimeter, so this is 10 to the power minus 10. Solve this. Sorry, 10 to the power plus 10, sorry. This is 10 to the power plus 10. 3 into 10 to the power 10. So this is the minus 24 and then to go up, so this is plus 10 into 10. 4112.4 divided by 6.626 into 3. So this, let's solve this. This is 206.88 per centimeter. So this is very close to this one, so this is the answer. Next question, I think one more remaining. Okay, last two questions now. Use Boltzmann distribution, the probability of an oscillator. Using Boltzmann distribution, the probability of an oscillator occupying the first two levels n is equal to 0 and 1 is found to be, okay, probability of 0th level is 0.637, probability of first level is given 0.223, and probability for n greater than or equal to 3 is given 0.042. So for 0, 1, 2, 3, 4 and so on. So the probability from here to here is given and for both is given, and we need to calculate probability at n is equal to 2 levels. Okay, we know that total probability is equal to 1, so that is equal to P naught plus P1 plus P2 plus P3 and so on. So this is all given. P naught is 0.6371 plus P1 is 0.223 plus P2, and this all quantity is 0.042. So P2 is 1 minus 0.637 minus 0.223 minus 0.042. So what will be the answer? 1 minus 0.637 minus 0.223 minus 0.042. So this is 0.098. So this is the answer. Last question. Okay, I have missed this question. So this is the last question for the class. In a sample of atomic oxygen at 27 degrees Celsius, what proportion of atom are in first excited state if it lie 1000 kilojoule per mole above the ground state? So delta E is given, that is equal to 1000 kilojoule per mole, and N1 by N naught is need to be calculated. So N1 by N naught is equals to e to the power minus E naught by kBt, and let's say it is 0, and then this is 1000 and this is E1 by kBt. So this is e to the power 0, that is 1, e to the power minus 1000 E1 by kb kilojoule. This is in kilojoule per mole. kb is 8.314 into temperature is 27 degrees Celsius, that is 300 Kelvin. So 300. So this is in kilojoule and this is in joule. So we need to balance this equation also. So 1010 to the power 3 divided by 8.314 into 300. So just calculate this. E to the power minus 10,000 divided by 131440 divided by 3 and divided by 8.314. So e to the power minus 400.93. So n1 by n naught is equal to e to the power minus 400.93. So it is not in the answer. So let's convert it in 10 to the power. So let's take ln on both sides. Ln n1 by n naught is equal to minus 400.93, and we know 2.303. If we multiply this by 2.303, it will be converted into log base 10, that is equals to n1 by n0, that is 400.93. So now from ln to log base 10, ln log base e to log base 10, it is just multiply it by 2.303. Now log base 10 n1 by n0 is equals to minus 400.93 divided by 2.303. 400.93 divided by 2.303. So it is minus 174.09 log base 10 n1 by n0. So n1 by n0 is equals to 10 to the power minus 174.09. So here it is the answer, minus 174.09. Thank you. This is all I have. This is the last tutorial. So thank you from my side. And if you have any problem, you can mail me, and I'll write my mail ID here. SHUBHAM Shubham 216122035 @gmail.com. This is my mail ID, and also my institute ID I will provide here, Shubham _ CHIITG @iitg.ac.in. You can contact me if you find any difficulty in solving any of these questions. I will upload these questions on the drive, and there will be only questions that I have solved. There is no solution for those questions. For solution, either you have to see the video, or you have to, if you find any problem after that also, you can mail me and I'll solve the question. Thank you. Thank you from my side.